Okay, let's get started, please. Welcome back, strangers, whoever you are. Okay, so we are going to get into the next chapter. This chapter is about eigenvectors and eigenvalues. Okay. So, in some sense, we could have gone right into this chapter from chapter 4. Chapter 5 was sort of a digression, but in fact, there'll be one point. If we make it to that point, we will need some results from chapter 5. Okay. So, but in some sense, it would have been pretty smooth to go right into here from chapter 5. Okay. Well, in any case, so let's start off with just the definition of the concept. So you have an n by n matrix. Okay. And for now, our matrices are going to be real, but soon we're actually going to allow them to have complex numbers. Okay. We are going to allow, so lambda is going to be a complex number, so I'll use C to denote the complex numbers, just like I use R for the real numbers. Okay, and we say that, if there exists a vector, a non-zero vector, such that, well, does anybody know what an eigenvector and an eigenvalue are? Have you heard these terms before? Anybody? What? I told you. What is it?
When you multiply something, it doesn't values don't change.
It doesn't what?
Oh.
Okay, so yeah, so you multiply. It's a vector that has a nice property that when you multiply it by the matrix, all that happens to it is that it gets multiplied by a scalar. Okay, it gets multiplied by a scalar. Okay. So, right, so, yeah, basically the vector just gets scaled. It's a special vector for this matrix, right? When the matrix hits it, all that happens to it is it gets scaled by some number. Okay. So if this happens, if there's a non-zero vector with this property, then we say that lambda is an eigenvalue of A, an eigenvalue of A, and that V is an eigenvector of A, eigenvector of A with eigenvalue lambda. Okay, and I tend to abbreviate eigenvalue as just eval, e-value, or eigenvector as just e-vector. Okay. Okay, so and we've seen these sorts of things before. If you remember the Markov chain thing, the Markov chain model, it turned out there were a couple of vectors that when you multiplied them by the matrix, by the transition matrix, then the vector didn't change at all. And there was another vector that only got scaled by 0.92. Do you guys remember that? So there were these two eigenvectors that showed up in that case. Okay. Okay. So here's an exercise for you to think about. If lambda is an eigenvalue, of A, then the set of eigenvectors corresponding to lambda is a substance. called the eigenspace. Called the eigenspace E sub lambda. Okay, so this E sub lambda, to put it in notation, E sub lambda is the set of all vectors such that AV equals lambda V. So it's the set of all eigenvectors with that eigenvalue. And I want you to think about it for a minute or two and try to convince yourself that that actually is a subspace. Okay, so convince yourself that that really is a subspace.
Can there be multiple eigenvectors that correspond to a single matrix?
Yeah, so corresponding to a single single eigenvalue, there actually will be infinitely many.
Okay.
Yeah. Yeah, so that's what so in fact there's going to be a whole subspace of vectors. Okay, turn to your neighbor and talk and say, I've forgotten what a subspace is. What is a subspace? How do we show something as a subspace? Do you remember what a subspace is?
It just can't be. Yeah, I think those are the rules of subspace.
Okay, so how do we show, what's a strategy for showing something as a subspace? How do you show something as a subspace?
Showing that it holds under multiplication, or scalar multiplication and addition.
Exactly. So you say, okay, we need to show that, suffices to show that this thing is closed under vector addition, and scalar multiplication. Okay, so let's do vector addition. Suppose that v1 and v2 are in E lambda, right? Is v1 plus v2 in E lambda? Is v1 plus v2 in E lambda? Well, what would have to happen? Right? We want to show, let's show that the sum is in E lambda. Being in E lambda means that you're an eigenvector that this guy's an eigenvector, right? Well, what do we need to do to show this guy's an eigenvector? We multiply it and see that we get lambda times it, right? So we say, okay, is it true that this thing equals this thing. Is that true? Sure, right? Sure. Andrew, you're nodding a little bit. Can I ask you to explain? Why is this true?
I was just going off the bat.
Oh, okay. Yeah. So, does somebody want to explain? Yeah.
There's a definition of an eigenvector that if some scalar v1 plus v2, or some vector v1 plus v2 is multiplied to the matrix, it'll produce lambda v1, v2.
Well, that's what we're trying to show. That's what we're trying to show. We're trying to show that, so we start off with this assumption that each of these guys individually is an eigenvector. We want to show that the sum is an eigenvector, right? So we know that AV1 is lambda v1. We know that AV2 is lambda v2. That's what we know. And we want to show that A times v1 plus v2 is lambda times v1 plus v2.
Well, if you distribute the A, then you
Sure.
get AV1 plus AV2, then we already know that that turns into lambda V1 plus lambda V2, and then you just pull the lambda back out.
Exactly, exactly. So you say, well, look, matrix multiplication distributes, right? So sure, right? AV1 v plus v2 is AV1 plus AV2, right? But just by matrix properties of matrix multiplication, right? Well, AV1 is lambda v1, and AV2 is lambda v2, since, right? So this part is since v1 and v2 are in v lambda, right? And then you just distribute again, right? You can pull a scalar out just by properties of multiplication. We have the distributive property, so we can distribute the scalar out. And so we're done, right? Okay, so pretty straightforward. Okay, so yeah, so that part is true. I want you to take 20 seconds and write down the second part, right? Suppose that V is in E lambda, and that alpha is a scalar. Is alpha v in E sub lambda? And you should be done. Okay, turn to your neighbor and say, this is what I wrote down. And the answer is sure, right? You just say, well, look, alpha, and it's like A alpha B is the same thing as alpha AV, right? You can pull out the scalar, right? Well, that's the same thing as alpha lambda V, right? Because V is in E sub lambda, right? And then you just change the order, right, by the associative property or something, right? No, commutative property, right? Okay, and you're done, right? So A alpha V is lambda alpha V. Okay, so you should be like, of course. Okay. Okay, so this thing E sub lambda, this eigenspace actually is a subspace. Okay. Now that's one proof. Here's a second proof, proof number 2. A different way, kind of cooler way to do it. You say, well, look, for something to be in E lambda is equivalent to saying that AV equals lambda V. AV equals lambda V. Okay. Okay, but that's the same thing as saying that AV equals lambda IV, right? lambda IV, where I is just the identity matrix. And I'm going to subtract from both sides. So I get A minus lambda I, and V equals 0. Right? I subtract this lambda IV from both sides, I end up with this, right? And I distribute out the lambda IV. I'm sorry, distribute out the V. Okay, so what does that say? That V is in this space if and only if this thing times V is 0, right? If and only if this thing times V is 0. Well, that means that V is in the null space, right? That's the same thing as saying that V is in the null space of A minus lambda I. Okay, so what is E sub lambda? Well, it's the null space of A minus lambda I, right? E sub lambda is the null space of A minus lambda I. Well, we already know that any null space is a subspace, right? We saw that earlier. So we have something a bit nicer. This guy is actually a null space of this matrix here. Okay, is that clear? Everybody all right with that? Any questions? Yes, Madeline.
Why do you have to multiply it by I?
Because to make it clear that this thing is in order to factor out the V, or I guess it's in order to make it clear that this is a matrix, right? This is a matrix. If I wrote A minus the number lambda, that would be kind of confusing. I'd have A minus a matrix minus a number, right? Which is it's true, but I want to think of this as think of this whole thing as a matrix, right? And so I replace it by lambda I, which does the same thing.
Okay.
Right? If I can't really talk about the null space of a number,
Mhm.
right? So. Okay, exercise number 2. So explain to me why a number lambda is an eigenvalue of the matrix if and only if the determinant of A minus lambda I is 0. I want you to think about that for a minute. Why is it true that an eigenvalue has to be something that makes the determinant of A minus lambda I equal to 0? Okay, talk with the neighbor for a minute.
Yeah, the determinant of V, that's essentially, so it's not
Okay, so what's the connection? What's the connection? What's the connection? Anybody? Can anybody give me some vague connection between the determinant of this thing being 0 and this guy being an eigenvalue? What is it? What if the determinant of this is 0? What does that tell you? If the determinant of something is 0, determinant of some matrix is 0, what do you know about that matrix? It's singular, right? It's not invertible, right? What other stuff do we know? Well, non-invertible means that something about
No inverse.
no inverse, yeah. The null space
Zero.
isn't 0, right? Then there's something non-zero in the null space, right? So the determinant of A minus lambda I being 0 is saying that there exists a non-zero vector, right? There exists a non-zero vector in the null space of A minus lambda I. Right? But we just said that the null space of A minus lambda I is the set of eigenvectors. Right? So what this is saying is that there's a non-zero V such that AB equals lambda V. Right? But that's the same thing as saying that lambda is an eigenvalue. Right? Lambda is an eigenvalue. Okay. So you start off with an arbitrary number, and you check this. If you get 0, then you know that that number was an eigenvalue. Sam, do you have a question?
No, I see.
Okay, clear? Anybody confused? Alec, how about you? Alex? You okay? Is it Alex or Alex? I'm sorry.
Doesn't really matter.
Doesn't
It's
matter.
Alec.
Alex, excuse me. There's a Alex in the next class who sits almost exactly the same chair. So okay. So everybody all right with that, right? You can a number is an eigenvalue if and only if A minus lambda I is non-invertible. In other words, the determinant is 0. Okay, so this gives us a way. This thing gives us a method, right? So we have a method of finding eigenvalues. We have a method of finding eigenvalues. So let me introduce a terminology. Given some matrix, we call the determinant of A minus lambda I the characteristic polynomial. The characteristic polynomial of A. Characteristic polynomial of A. So, and in this we're thinking of lambda as a variable. Okay. We think of lambda as a variable. right? So this lambda is varying, right? And sometimes, so you get this polynomial, you get a polynomial lambda. You get a polynomial lambda, and we're going to look for when that polynomial is 0, right? We're going to look for what lambda makes that polynomial 0. So the eigenvalues of A are the lambda for which the characteristic polynomial equals 0. Right? In other words, they are the roots of the characteristic polynomial. Right? The roots, the zeros of the characteristic polynomial. Okay, so just to give you a simple example, if I give you a matrix 6, -4, 3, -1, then the characteristic polynomial would be the determinant of A minus lambda I. Well, that's going to be 6 minus lambda, -4, 3, -1 minus -1 minus lambda. I'm sorry, the determinant of that. Okay, so this thing would be the characteristic polynomial. In other words, 6 minus lambda times -1 minus lambda minus 3 times -4. Right, whatever that is, it works out to lambda squared minus 5 lambda plus 6. Okay, so to your matrix, you associate a polynomial. And that polynomial is called the characteristic polynomial, right? What are the roots of this? What are the roots? Looking at it, go back to junior high school. What are they? Can you just look at it and tell me? 2 and 3, yes. So this is this minus 2, this minus lambda minus 2 times lambda minus 3. So it has roots 2 and 3. Okay. So that tells you that, right, that the determinant of A minus 2i is 0. The determinant of A minus 3i is 0. In other words, these guys are the eigenvalues of A. So these guys are the eigenvalues. So that gives us this gives us a method for finding the eigenvalues. Now, once we have the eigenvalues, we can find the eigenvectors, right? So the eigenvectors, we can then find the eigenspaces, right? Because remember, E sub lambda is the null space of A minus lambda I. Right? We saw earlier. Okay, so we just need to take the cases, right? When lambda equals 2, E sub 2, right, is going to be the null space of A minus 2i, right? So that's going to be 3, -4, right? I'm sorry. Is that A minus 2, 4, -4, 3, -3. Right? Well, now you have to remember how to find the null space. Well, we've been doing this all term over and over, finding null spaces. So you say, okay, I've got this matrix here, 4, -4, 3, -3. I'm going to do Gaussian reduction on it. You see what's going to happen, right? This guy's going to become 1, -1, and the second row will vanish, right? Because it's dependent on the first row, right? So you get You reduce it, you get 1, negative 1, 0, 0. Right? So that gives you the equation x1 minus x2 equals 0. Right? So your null space looks like x1 equals x2, right? So you get the x1 minus x2 equals 0. So the span of 1, 1 is E2. Okay. Dave, what's wrong?
Yeah,
No, you okay? Okay. And then for the other guy, for lambda equals 3, well, you're going to get 3, negative 4, 3, negative 4, right? We want the null space of A minus 3i, which equals this thing. Right? Which reduces, of course, to 1, negative 4/3, 0, 0. And so you get that x1 equals 4/3 x2. In other words, 4/3 1. The span of this is going to be E3. Okay. You guys are looking a little bit less bored than I think you should. Yes, please.
But I'm a little confused about the jump, like the x1 minus x2 equals 0. Like you reduce it and then.
Right, so we get down to here.
Mhm.
So this is what system corresponds to this? Right? This is x1 minus x2 equals 0, 0 x1 plus 0 x2 equals 0.
Okay.
Right? We're looking for the null space of this, right? That is to say that 1, negative 1, 0, 0 times x1, x2 equals 0, 0. Right? So we need x1 minus x2 to be 0, and the second equation is satisfied. Trivial. Somebody has a, yes, Sam.
So when you're subtracting like 2 or 3i from A,
Yeah.
it's like the trend I see is like for 2i you're subtracting 2 from the diagonal.
Yeah, because what's 2i, right? 2i is 2 times 1, 0, 0, 1.
Okay, yeah.
Okay,
My
that's
bad.
2.
Yeah. No, that I got
That's
that.
okay. I should have spelled it out.
Yeah, and then my other question
Yeah.
is that, so for 2, you said the span is 1, 1.
Yeah, the span of the vector 1, 1, right? Because our equation was x1 minus x2 equals 0,
Yeah.
right? That tells you that x1 is x2, right? That tells you that your vector looks like this, x2, x2,
Yeah.
right? x2, x2, in other words, some multiple of 1, 1.
Yeah.
Right? Any solution is going to be some multiple of 1, 1, right? It's going to be in the span of 1, 1.
Yeah.
Okay. 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 Let me give you something, an exercise to think about for a minute. If lambda is an eigenvalue of A, then lambda to the k is an eigenvalue of A to the k. Okay, talk with somebody nearby.
Yeah. Probably for induction. Yeah, and then you assume straight for A, B to K.
Okay, would somebody like to talk about it? So let's say that lambda is an eigenvalue of A. Right. In other words, there exists a non-zero vector such that AB equals lambda V. So we want to show that lambda to the k is an eigenvalue of A to the k. Yeah.
Do you use proof by induction?
By induction? Maybe, possibly. Yeah, go on.
I mean, since you know like AV is equal to lambda V,
Yeah.
that's like your base case.
Yeah.
And then you can assume it's true for A, V, A to the K minus 1 times V is equal to lambda to the K minus 1 times V, and then you just prove the
That'd
last
be great.
step.
Yeah, that'll do it. So you can, okay, so yes, you can. By induction, you say, well, look, I already know that AV equals lambda V. So, right, case K equals 1 is done. So assume that A K minus 1 V equals lambda K minus 1 V. Right? And then apply any of those signs. You get A to the K V equals A lambda K minus 1 V. Right? But you can interchange these guys. You can pull out the constant, so you get K minus 1 AV. But we know that AV is KV, is lambda V, right? And so we get lambda to the KV. Right? So we assumed the K minus 1 case, and we get the kth case. So done by induction. Basically, it's noticing that you can just keep applying A. Right? If this is true, then hit it with A again. Right? You get A squared equals A lambda V. You can pull the lambda out and get lambda AV. But lambda AV is lambda squared V. Right? So you're done. And you get the second case, and you just keep on applying lambda. Right? But to do it properly, you'd use induction. Okay. Some observations. Okay. Now these observations, I have the word simple, but then I have a question mark after it. Simple observations. I think maybe they're not so simple. So, because they involve something called the complex conjugate, which we haven't introduced yet. But does anybody know what the complex conjugate is? Like you have some complex number, z equals a plus bi, right? Where a and b are real numbers. Right? You have like 3 plus 4i, for example, right? And you take this thing called the complex conjugate. What's a complex conjugate? You take this thing, z bar, complex conjugate. Complex conjugate of z is called z bar, denoted z bar. Anybody seen this before? Anybody? Louisa, what is it?
A minus bi.
Exactly, a minus bi. A minus bi. Right? So, on the complex plane, right, you've got your a plus bi, right? You got your a plus bi. Right? This is the real axis. This is the imaginary axis. And then you've got this thing a minus bi, which is the complex conjugate. Okay, so it's the reflection across the real line, of the point. Right? And you see that if I took the complex conjugate of z bar, I would flip back to z, right? Z, the complex conjugate of the complex conjugate of the complex conjugate will be the original point. Yeah, Jake.
What would be a reflection over the imaginary line?
Yeah, so that would be, well, what would happen? The A would become negative A, right? So you get negative A, the B would stay the same, right? But you would get negative A plus BI. Okay, so you would flip that. You would flip the real part rather than the imaginary part. I'll give you a point on the final just for asking that peculiar question. Okay. Okay, 5 more minutes. Let's see. So, okay. Okay, so here's simple observation number 1. If lambda and no. Okay, we're going to have to start up with the more complicated of the simple observations. If lambda, the complex number lambda, is an eigenvalue, so A is a real matrix, and this is important, A is a real matrix. If lambda is an eigenvalue, then so is lambda bar. And so is lambda bar. Okay, so why? So lambda being an eigenvalue is equivalent to saying that the determinant of A minus lambda I equals 0. Right? The determinant of A minus lambda I equals 0. Okay. So I've got some polynomial over here. Okay. And it's the determinant of it is 0, right? So this is some polynomial. Right. Okay. So now I'm going to take the complex conjugate of both sides. Take the complex conjugate of both sides. So I take the complex conjugate of this polynomial, right? So, if I had some polynomial over here, right? Right? I just take the complex conjugate of both sides. Okay, and I would get lambda bar squared minus 5 lambda bar plus, I would get this. Okay. So I'm kind of cheating you because I'm using a property of the complex conjugate, but I'm just gonna do it. Okay. But what happens if you take a real number and complex conjugate it? Well, you're sitting on the real line and you flip yourself across the real line. Where are you? In the same place. Right? You don't move at all. Right? So this 5 and the 6 don't change. Right? So 5 and 6 don't change. Right? So what does this tell me? Right? This tells me that lambda bar satisfies the original polynomial. Right? If lambda satisfies the original polynomial, well then lambda bar. So if lambda satisfies this original equation, well then lambda bar is going to satisfy the equation also. Okay, so any root of the complex conjugate, any root of the characteristic polynomial its complex conjugate is still going to be a root with a characteristic polynomial. Okay, I hope that's at least vaguely believable. Okay, so you say, okay, well, what it boils down to here is like this. You get the determinant of A bar minus lambda bar I equals 0. But since A is a real matrix, this is the same thing as A. Lambda A bar is the same thing as A. Okay, and so what you see is that, right, if lambda is an eigenvalue, then lambda bar is an eigenvalue. Okay, so now I'm cheating you to some degree because I'm using properties of the complex conjugate, a simple property of the complex conjugate, but I didn't really explain it. So maybe you have to sort of trust that this sort of thing happens. This sort of thing is true. Actually, does happen. But it's not hard to say. So anyway, so whenever you have an eigenvalue, then lambda bar is also going to be an eigenvalue, right? As long as your matrix is a real matrix. Not true if your matrix is complex, though, right? Because then when you take the bar of it, your matrix changes, right? You don't get the determinant of A anymore. Because what would happen would be that this 5 and 6 might be complex numbers, right? And then things change. Okay, let's stop. There's another observation. I'll remind you of this tomorrow, next time, and then we'll go on from there. Oh, I have exams for you if you want to. Maybe you don't want.